Assalamualaikum warahmatullahi wabarakatuh to our lecturer and everyone. Today our group will present our project titled IoT-Based Real-Time Flood Risk Monitoring and Early Warning System. This project combines artificial intelligence (IoT) MQTT communication and the ThinkBox cloud platform to monitor environmental conditions and provide early flood risk warning. Before I go through detail about our project, I will introduce our group member. First, Aizul Fahan bin Anzwar. Second, me, Muhammad Alif Najmi bin Iswandi. Third, Muhammad Imran bin Zamri. Introduction. Flooding is one of the major natural disasters in Malaysia. For this project, we focus on Hulu Terengganu because this area is vulnerable to flooding, especially during the northeast monsoon season. Flood risk can increase because of heavy rainfall, rising river level, and river overflow. However, traditional monitoring method may depend on manual observation, which can delay flood warning. Therefore, we propose using IoT and AI to support real-time monitoring and early flood prediction. We go through the problem statement. The main problem is that some flood monitoring methods still rely on manual observation and delayed reporting. As a result, warning information may not reach the affected community early enough. Another problem is that weather data and water level data are often analyzed separately. This makes it more difficult to understand the overall flood condition. Therefore, our proposed solution combines IoT, AI prediction, and a cloud dashboard in a one centralized system. The goal is to provide faster flood risk assessment and support better decision making. Next, project objective. This project has five main objectives. First, to develop a virtual IoT engaged client using Python in Jupyter Notebook. Second, to stream environmental telemetry data to a cloud platform. Third, to establish communication between Jupyter Notebook and TeamSboard using MQTT. Fourth, to create an interactive dashboard with monitoring, widgets, and warning indicator. Finally, to analyze the relationship between weather condition and change in river water level. We move to purpose system scope. The system uses five main input parameters. These are rainfall, temperature, humidity, wind speed, and water level. The data is processed by the AI model to determine the probability and severity of flood risk. The system produces four possible risk categories, which are normal, alert warning, and danger. The results are then displayed through the ThinBoard dashboard for real-time monitoring. Overall methodology. The methodology consists of six main stages. First, environmental data is collected from online source. Second, the historical data set is prepared, cleaned, and labeled. Third, the dataset is used to train the AI prediction model. Next, the processed telemetry data is sent through MQTT. The data is then displayed using TeamBox. Finally, the prediction, result, and alarm functions are evaluated to determine whether the system works correctly.
Okay, thank you, Alip. Now let's dive straight into our technical execution. Starting with our dataset preparation and risk level thresholding. All collected environmental and historical feature we clean and structure into a unified CSV dataset, where we isolate our core input from the target class. To training our system, we establish for strict water level threshold based on historical risk pattern. Any water level below 6.0 meter is labeled as normal. Between 6.0 meter and 6.5, trigger can alert state. 6.5 to 7.5 acts as a warning, and anything exceeding 7.5 is discretely categorized as a danger zone. Okay, moving on to our AI model development. In our Jupyter Notebook environment, we utilize Python alongside advanced data science library like Pandas and scikit-learn. We split our dataset using a standard 20% radiation size and train a random forest classifier with 100 estimators. We specifically selected random forest because it leverages ensemble learning, constructing multiply decision trees to average the prediction variance. This handles multivariable, nonlinear environmental data exceptionally well and mitigate any risk of overfitting. The model evaluates life metric to compute not just the exact flood risk category, but also its mathematical probability percentage. Next, let's look at the IoT and MQTT integration, which bridge our AI engine with the cloud infrastructure. We established a low latency publisher subscriber network architecture where our Python environment acts as the MQTT publisher. The moment our random forest model generates a predictive output, the script serializes this variable into a structure JSON payload. It then initiates a square connection to the ThingsBot cloud, authenticating directly via the device unique access token. ThingsBot acting as our centralized MQTT broker, instantly parse the incoming telemetry stream in the real time. Now, looking at our dashboard and alarm system. Once these bots subscribe to and process the JSON telemetry, it dynamically updates our live visual ecosystem. We have designed a user-friendly, centralized dashboard that features interactive digital gauge for immediate data reading, a geographical map marker to track, historical data, graph, and automated alarm state widget. If the incoming AI prediction is a critical percentage, the alarm widget is instantly change color and status to alert the operators. So now let's evaluate our actual system result and analysis, which perfectly demonstrate the contextual intelligence of our model. If you look closely at the dashboard, the current rainfall registered at an extremely negligible 0.1 millimeter under traditional rule-based threshold system. This low rainfall would be ignored. However, our random forest engine has accurately triggered a critical danger status with a 97% flood probability. Why? Because the model recognized that the river water level had already breached the critical danger line at 7.6 meter. Override the low rainfall factor. This proves our system does not just display raw data. It understands complex data correlation, making it a highly reliable predictive tool for proactive disaster management. To conclude our presentation, our project successfully demonstrates that combining random forest predictive analytic with this board IoT simulation create a highly reliable real-time flood monitoring pipeline. For future improvement, we plan to enhance this system by automating our Python script to run continuously on cloud server like AWS and integrating automate alert like Telegram or SMS notification to directly notify high-risk communities. So that's all for me and from our group.
Project. This show that Tinkerbell cloud that we made. This is a location map that I pinned at Kampung Seri Putera Badak. This show that temperature, humidity, wind speed, flood risk, and the status that at the place. The dashboard also show that river level trend, rainfall, and temperature and humidity. For the red line for temperature and the blue line for humidity. This chart is always update by the time.